Dear students, in this section, we introduce the notion of cosets of the subgroups of a group. The study of cosets leads immediately to Lagrange's theorem, which is one of the most fundamental theorems in the theory of groups. The notion was invented by Galois in 1830, although the term was coined by G. A. Miller in 1910. Let us see the definition of coset. Let G be a group and H be a subgroup of G. For any A in G, the set AH is equal to AH such that H in H is called the left coset of H in G containing A. Analogously, HA is equal to the set HA such that H in H is called the right coset of H in G containing A. Here the note is, if the operation in G is addition, then the left coset A plus H is equal to A plus H, where H in H, A in G. Similarly, for right coset in G. Let us see some more examples of cosets. The example is, suppose Z is the group of integers with respect to addition and H is the subgroup of G consisting of all multiples of 4. Then the right cosets of H are the sets H, H plus 1, H plus 2 and H plus 3. Clearly, these are also the left cosets of H. In the above example, we may consider the subset consisting of all multiples of any fixed integer n. Let H is equal to the set 0, 3, 6 in Z9 under addition. In the case that the group operation is addition, we use the notation A plus H instead of AH. Then the cosets of H in Z9 are 0 plus H is equal to the set 0, 3, 6 is equal to 3 plus H is equal to 6 plus H. 1 plus H is equal to the set 1, 4, 7 is equal to 4 plus H is equal to 7 plus H. The set 2 plus H is equal to the set 2, 5, 8 is equal to 5 plus H is equal to 8 plus H. These examples illustrate a few facts about cosets that are worthy of our attention. First, cosets are usually not subgroups. Second one is, AH may be the same as BH even though A is not same as B. But AH need not be the same as HA. See some remarks here. The remarks are, any two cosets are either identical or else have no element in common. In other words, if two cosets have an element in common, then they are identical. If the left cosets and right cosets are the same, then H is normal subgroup and the cosets form a group called the quotient or factor group. For example, the center Z of G of a group is always normal. In abelian groups, left cosets and right cosets are always same. The coset 1H is simply the subgroup H. In fact, for any H in H, since H is closed under multiplication, the coset HH is equal to H. Let us see some of it. Properties of cosets as a following result. The result is, let H be a subgroup of G and let A and B belong to G. Then the first property is A belongs to AH. The second one is AH is equal to H if and only if A in H. Third, AB into H is equal to A into BH and H into AB is equal to HA into B. The fourth one is AH is equal to BH if and only if A belongs to BH. The fifth one is AH is equal to BH or AH intersection BH is equal to empty. The sixth one is cardinality of AH is equal to cardinality of BH. Seventh one, AH is equal to HA if and only if H is equal to A inverse HA. The eighth one is AH is a subgroup of G if and only if A in H. Let us prove here. The first one, A in AH is trivial since A is equal to AE in AH, where E is the identity of G. The second one, to show AH is equal to H if and only if A in H. Suppose AH is equal to H, then A is equal to AE in AH is equal to H. Now assume A in H. Since H is closed, AH is subset of H. Next assume H in H also. A inverse H in H since H is subset of G. Then H is equal to EH is equal to A inverse into H is equal to A into A inverse H in AH. So H is the subset of AH. Hence we have AH is equal to H. The third one, to show that AB into H is equal to A into BH and H into AB is equal to HA into B. The fourth one, this follows directly from AB into H is equal to A into BH and H into AB is equal to HA into B. To prove the next property AH is equal to BH if and only if A in BH. Let AH is equal to BH, then A is equal to AE in AH is equal to BH. Conversely, if A in BH, we have A is equal to BH where H in H and therefore AH is equal to BH into H is equal to B into HH is equal to BH. The fifth one, to show all AH is equal to BH or AH intersection BH is equal to empty. We suppose that AH intersection BH is equal to empty and let X in AH intersection BH. Then there exists H1, H2 in H such that X is equal to AH1 and X is equal to BH2. Thus, A is equal to BH2 H1 inverse and AH is equal to B into H2 H1 inverse H. By property 2, AH is equal to H if and only if A in H we have AH is equal to BH. Hence, AH is equal to BH or AH intersection BH is equal to empty. In other words, it follows directly from property 4. For if there is an element C in AH intersection BH, then CH is equal to AH and CH is equal to BH. Sixth one, consider alpha from AH mapping to BH defined by alpha AH is equal to BH. This is clearly onto BH. Suppose alpha AH1 is equal to alpha AH2. Then BH1 is equal to BH2. This implies H1 is equal to H2 by left cancellation. So, alpha is 1 to 1 since alpha provides a 1-1 correspondence between AH and BH. Hence, cardinality of AH is equal to cardinality of BH. The seventh one is to show AH is equal to HA if and only if H is equal to A inverse HA. Note that AH is equal to HA if and only if AH A inverse is equal to HA A inverse is equal to H A inverse is equal to H. That is, AH is equal to HA if and only if AH A inverse is equal to H. The last one is AH is a subgroup of G if and only if A in H. If AH is a subgroup, then it contains the identity 9. Thus, AH intersection EH is not equal to empty. And by property 5, we have AH is equal to EH is equal to H. Thus, from EH is not equal to empty, and by property 5, we have AH is equal to EH is equal to H. Thus, from property 2, we have A in H. Conversely, if A in H, then again by property 2, AH is equal to H. Now, can we relate the cosets with normality? Cosets and normality. If H is not normal in G, then its left cosets are different from its right cosets. That is, there is an element A in G such that no element B satisfies AH is equal to HP. This means that the partition of G into the left cosets of H is a different partitions than the partition of G into the right cosets of H. It is important to note that some cosets may coincide. For example, if A is in the center of G, then AH is equal to HA. On the other hand, the subgroup N is normal if and only if Gn is equal to Ng for all G in G. In this case, the set of all cosets from a group called the quotient from G by N with the operation star defined by An star Bn is equal to Abn. Since every right coset is a left coset, there is no need to differentiable left cosets from right cosets. Now we are going to learn about number of cosets in the name of index, that is index of the subgroup. The index of H in G is defined as the number of cosets of H in G. It is always the case that the number of left cosets of H in G is equal to number of right cosets. This number is denoted by this. This means, it means index of H in G. If the index of H in G is 2, then H must be a normal subgroup of G. Some examples of index of the subgroup. Let Z be the group of integers under addition and let 2Z be the subgroup of Z consists of the even integers. Then 2Z has two cosets in Z, namely the even and odd integers. So, the index of 2Z in Z is 2. To generalize, the index of nZ in Z is equal to n for any positive integers n. Some remarks of index like this. The remarks, if G is infinite, the index of a subgroup H will be in general be a non-zero cardinal number. It may be finite. A positive integer is the index as the example above shows. The example already we have told. If G and H are finite groups, then the index of H in G is equal to the quotient of the orders of the two groups. Index of H in G is equal to cardinality of G divided by cardinality of H. Next one is properties of index. Index satisfies transfer inequality. This states that if H, K subgroup of G, then the index of H intersection K in K is less than or equal to the index of H in G. Next, index is multiplicative. This states that L is subgroup of K subgroup of G, then the index of L in G is equal to the product of the index of K in G and the index of L in K. Let us see some theorems. The first one is index satisfies intersection inequality. Suppose G is a group and H, K are subgroups of finite index in G, then we have the index of H intersection K in G is less than or equal to the product of the index of H in G and the index of K in G. And analog statements holds for subgroups of infinite index provided we interpret the indices as infinite cardinals. Let us prove it here. Let us prove here by property 1, if H, K is subgroup of G, then the index of H intersection K in K is less than or equal to the index H in G. We have the index H intersection K in K is less than or equal to the index H in G. Setting L is equal to H intersection K in property. The second one is L is subgroup of K is subgroup of G, then the index of L in G is equal to the product of the index K in G and the index L in K is the index H intersection K in G is equal to the product of the index K in G and the index of H intersection K in K. Combining these yields, the index of H intersection K in G is less than or equal to the product of the index of K in G and the index of H in G, which is equal to the product of the index of H in G and the index of K in G. Cosets are a basic tool in the study of groups. For example, they play a central role in Lagrange's theorem. What is Lagrange's theorem? We will see here. If G is a finite group and H is a subgroup of G, then cardinality of H divides cardinality of G. Moreover, the number of distinct left or right cosets of H in G is cardinality of G divided by cardinality of H. Let us prove the theorem here. Let A1H, A2H and so on ARH denotes the distinct left cosets of H in G. Let A be an arbitrary element in G. We have A, we have AIH for some I. Also, A is equal to AE in AH, where E is the identity. Thus, each member of G belongs to one of the cosets AIH in symbols. Now, G is equal to A1H union A2H union and so on union ARH. Now, by the property that either AH is equal to BH or AH intersection BH is equal to empty, we have the union A1H union A2H and so on union ARH is disjoint so that the cardinality of G is equal to the cardinality of A1H plus the cardinality of A2H plus and so on plus the cardinality of ARH. Finally, since the cardinality of ARH is equal to the cardinality of H for each I, we have the cardinality of G is equal to R into the cardinality of H. Hence, the cardinality of H divides the cardinality of G. Lagrange's theorem has many important applications in group theory. For example, a group of order 3, 5, 6 or 7 for they do not divide 8. In fact, any non-trivial subgroup of this group must be of order 2 or 4. It is essential to point out that the converse of Lagrange's theorem is false. That is, if G is a finite group of order n, if M is a divisor of n, then G need not have a subgroup of order M. Cosets leads partition. Having considered several examples of subgroups and their cosets, we will now prove that the various things that those examples were observed to have in common are true in general. We will limit our attention to groups of finite order. Specifically, we will prove that if G is a group of finite order and H is a subgroup of G, then the collection of distinct left cosets of H partition G into sets which all have the same number of members. The same is true if we consider right cosets instead of left cosets, although the partition obtained might be different if the group G is not abelian. Recall that a partition of a set A is a collection of non-empty subsets of A such that each member of A belongs to exactly one of these subsets. Abstract visualization of partition of group is like this. We are in the conclusion of this today module. In this module, we have learned about the structure of cosets and index of subgroup of a group. Today we have seen the definition of cosets and index, then verified its properties with the constructed proof. After that, we have proved the important theorem called Lagrange's theorem. Finally, we discussed how the group will be partitioned through the cosets. Hope you have enjoyed today's class. We will meet again. Thank you.